Alright, so starting with the warm-up in lesson 4 here, it says the table represents the values of the function f. And let me grab a pen here before I continue. The values of the function f. The function is continuous on the closed interval and differentiable on the open interval from 0 to 15. Alright, it says, does f of x ever equal 27? Well, if we start to look at the values here, we definitely have a value where f of x has to equal 27 in here, because remember, it's continuous and differentiable. Alright, and then we go from 34 to 30, then we go from 30 back down all the way to negative 32, so we're going to hit 27 in there again, and then negative 32 to negative 8, and then we go negative 8 to 30, okay, and then 30 back down to negative 4. Wow, we got a whole bunch of places where it equals 27 in here. So it doesn't ask us for all of them, it just says does it ever equal 27. So we could mention all of them, or we could just mention one of them. Alright, so I'm going to just do the first one that I found right here, and so my answer is going to be yes. Alright, now the reason we know it has to equal 27 is because we're continuous on the interval. Saying we're differentiable implies that we're continuous, okay? Because in order to be continuous, you have to be differentiable, all right? So differentiability implies continuity, so we would say yes, because f of x is differentiable on the interval from 0 to 15, and this is the open interval, 0 to 15, and f of 1 equals 25, and f of 3 equals 34, then there exists a c in the interval from, and we can narrow this one down, in the interval from 1 to 3, such that f of c would equal 27. How do we know this? This is IVT, intermediate value theorem. Okay? And so if you look at letter B, it says what is the minimum number of times that f of x equals 0. So now I'm going to go back and erase a little bit here. So now we're looking at 0 and the minimum number of times. Now if you let's just kind of take a look here. We go from 12 to 25, so we're looking for where f of x goes from positive to negative, basically. So my first interval is going to be right here from 30 to negative 32, or on the interval 6 to 7, I go from 30 down to negative 32. So I have to equal 0 in there. Now, could I equal 0 in some of these other ones? Yes, I could, but I don't know any other information about it. So when it says the minimum number of times, we're looking at, I know it has to equal 0 from 30 to negative 32, and then I know it's going to have to be 0 at negative 8 and 30, and then again from 30 to negative 4, and again from negative 4 to 6. It's got to hit 0. So let me just recount those real quick, because my number in my notes are showing 3 times. So we're going to go from 30 to negative 32, so we're definitely going to hit 0. Negative 8, negative to positive, positive to negative, and negative to positive. So it looks like it's 4 times here. So I got a 4 times. So that's the first thing I want to say. Okay? Give me 1 second. Alright. So the reason we know this again, we have to start out with the fact that we know that f of x is differentiable. Alright, so we're going to say since f is differentiable, and we're saying that because therefore we know it's continuous on 0 to 15, and f goes from positive to negative, or negative to positive on these intervals, okay? And so we're going to list them: 6 to 7, 10 to 12, and 12 to 14, and 14 to 15. Okay, so we're either going positive, negative, or negative to positive on those. Then there exists, there exists a C in each interval. All right, so in each interval, such that f of c equals 0. How do we know this again? IVT. All right. Our last question says, and I'm going to read it while I'm looking at the chart here, okay? Is there an interval where f prime of c equals 0 for some c on that interval? If yes, give the interval in a justification. So again, it's saying, is there an interval where the derivative is equal to 0? Okay? That means that f of x has to either go from increasing to decreasing or decreasing to increasing. Okay? So I need to find an interval where f of x goes from increasing to decreasing or decreasing to increasing. Okay? And let's see here. All right, so let's see here. If I look at the interval, now I'm looking for where f is going from increasing to decreasing. So if we look at 0, we've gone from 12 to 25 to 34. We're constantly increasing there, but all of a sudden we go from 34 back down to 30. So if I look at this particular interval right here, I know that f went up in that interval, and then I know that f went back down in the next interval. So somewhere in there, we went from increasing to decreasing. All right? So increasing to decreasing. So we could use the interval from 1 to 6. All right? Now, in order for me to do this, I'm going to lose that. So is there an interval? So yes. And I got to remember what we were talking about here. So on the interval from, I shouldn't even say from, on the interval 1 to 6, f goes from increasing to decreasing, which implies that f prime, well, let me keep going here, which implies that f has a max, so there exists a c in 1 to 6 such that f prime of c equals 0. All right? So if f has a max, there has to be a c in that interval. Now, if you look at your chart, and I'm going to scroll back up here for a minute, we could have also used mean value theorem here. All right? So take a look at the chart again. I'm going to go back and make some new marks in here, but if I look at the question again asks, is f prime of c equal to 0? So if you look at the interval from, let's see here, look at this interval from 6 to 12. All right? Look what happens if I take the average over that interval. All right? So if I were to take the slope over that interval, I'd have 30 minus 30 over 12 minus 6. So if we look at it like that, okay, so we'll put a little line there to separate these. So I could have also said yes, on the interval, I learn how to write here, on the interval 6 to 12. All right, we know that f of 12 minus f of 6 over 12 minus 6 would equal 0 over 6, which equals 0. Since f is differentiable on 0 to 15, then there exists a c in 6 to 12 such that f prime of c is equal to 0. And our reasoning here would be mean value theorem. Okay, so either one of those would get you to where you need to be on this one. All right, let's take a look at another curve here today. All right, this one's a little more familiar maybe, but it's got a little more going on than the previous lesson. All right, so we're going to use critical numbers again for f of x, or f prime of x, f double prime of x. We're going to find increasing, decreasing, all that kind of stuff, and we're going to sketch f of x here. All right, so first thing we're going to start off is the regular stuff. What's the y-intercept here? So we can do a y-intercept. I know that that's going to be, if I plug in 0 here, I'm going to get, well, let's do this, 0 comma, and I'm going to end up with 18 over negative 18 over negative 4, which is 9 halves. So I have a y-intercept at 9 halves. An x-intercept, this one I'm going to have to do a little work here. So we plug in 0, we get 2 times x squared minus 9 all over x squared minus 4. So again, I'm going to cross multiply here. I get 0 coming across one way, and 1 times the numerator on the right side is 2 times x squared minus 9. I'll go ahead and divide by 2 on both sides here, so that's going to give me 0 equals x squared minus 9, and I can actually get rid of the parentheses now. X squared minus 9, add 9 to both sides, x squared equals 9, so x is equal to plus and minus 3. So I'm going to have 2 x-intercepts, one at 3, 0, and one at negative 3, 0. Okay, let me see the domain for this guy here. We know we're going to be, let's talk about domain here. Domain, we've got some restrictions on our denominator here, and we could factor out the numerator and the denominator and take a look at those, but basically our domain is going to be restricted that x cannot equal positive or negative 2. So we've got something going on there. We'll take a look at those. All right. We also want to take a look at, well, we'll do those now. So I talked about factoring that. Let's go ahead and factor that just so you can see this. So f of x, if we factor the numerator, we get 2 times x minus 3 and x plus 3. So if you remember back from Algebra 2 and pre-calc, factoring the denominator, x plus 2, x minus 2. All right, we don't see any factors that cancel, so there's not going to be any removable discontinuities, no holes in our graph, but we do have 2 vertical asymptotes. Those are the restrictions in our domain that I was just talking about. So these 2 factors in the denominator actually give us vertical asymptotes at x equals positive and negative 2. All right, so we know that. And let me see, what about right and left behavior? So we need the limit as f of x, the limit as x goes to positive and negative infinity. Now I can do this one together because if you remember your rules, again from Algebra 2 and pre-calc, when I go back to look at this function, I'm looking at the leading coefficients of my numerator and denominator. Now you can plug in values in a t-table and find the same thing, but that's basically 2x squared over x squared, and 2x squared over x squared gives me a limit of 2. So what we're saying here is we have a horizontal asymptote at y equals positive 2. All right? So that's the basic stuff that we already know about. And we'll go down and graph it all in a minute, but let's take a look at our derivatives first. All right, so f prime of x. So I need the derivative for f. Now, it looks like we got a little bit of our quotient rule going on here. So we're going to take, let's see, we're going to take the derivative of the numerator. So that's going to be 4x and times the denominator. That's going to be x squared minus 4. Sorry, I have to look back and forth because I can't see up top anymore. 4x times x squared minus 4, and then, minus the numerator, which is 2 times x squared minus 9, times the derivative of the denominator, that's going to be 2x, all over the denominator squared, so that's x squared minus 4 squared. All right. Now, I'm going to need to clean this up a little bit in order for us to do something with this. And we're just going to have to clean it up. There's nothing that we can cancel out here at this point. So let's clean up the numerator and see what happens here. So we're going to end up with 4x cubed minus 16x. On the right side, you've got the 2x times the 2, so that's going to be 4x. And then 4x times x squared is going to be negative 4x cubed. And then 4x, well actually it's negative 4x times negative 9 is going to be positive 36x. So that's my numerator. And my denominator is still x squared minus 4 squared. So cleaning up the numerator, it looks like we're going to end up with the 4x cubes canceling. Negative 16x plus 36x is 20x. And then my denominator is x squared minus 4 squared. Okay? So let me see. The first thing we want to look for is critical values again. So we are undefined. So what makes my denominator equal to 0? We're undefined at x equals plus and minus 2. And if you set this equal to 0, you're going to end up with, well, I'll show the work here. So if we set it equal to 0, we get 0 equals 20x over x squared minus 4 squared. If you cross multiply that, you get 20x equal to 0, which means that x is equal to 0. So there's our 3 critical values on this one. So I'm going to go down here. We're going to start with 0. We'll look at negative 2 and positive 2. And so now what we want to do is we want to look and see whether f prime is positive or negative. So we're going to look at f prime of x. So to the left of negative 2, we'll try x equals negative 3. In between negative 2 and 0, we're going to try x equals negative 1. Between 0 and 2, we'll try x equals 1. And from 2 to infinity, we'll just try 3. All right, so we need to plug each one of these values into f prime and see whether f prime is positive or negative. Now, if you check it out, look at my last fraction here. If I plug negative 3 into the numerator, that's going to be negative 60, so that's negative. I don't care if it's what the number is. Look at your denominator, though. The denominator here is always going to be positive because no matter what I get in the parentheses, I'm going to square that, and so the denominator is going to be positive. So negative over positive is going to leave me negative in this interval, from negative infinity to negative 2. If I plug in negative 1, my numerator is negative again. My denominator is positive, which means that f prime is negative here. If you plug in positive 1, the numerator is now positive. The denominator is always positive, so f prime is positive. And the same thing happens when you plug in 3. Numerator is positive, denominator is positive. So here we go. All right. So what we're looking at is f of x. We want to know what f of x is doing. So f of x, if f prime is negative, we know that f of x is decreasing. So we're decreasing from negative infinity to 0. Then we're increasing from 0 to infinity. All right? So that's f of x. Let's look at f double prime of x. All right. So f double prime, taking the derivative of f prime of x, I'm using my simplified fraction over here. So the derivative is going to be, and we got some quotient rule here again, so it's going to be derivative of the numerator, 20, times the denominator, x squared minus 4 squared, minus the numerator, 20x, times the derivative of the denominator. Okay, I got to be careful on this one here. So we're going to end up with some chain rule going on here. The derivative of the denominator is going to be, let's see, we've got 20x times 2, bringing the exponent from the denominator down in front, times x squared minus 4, times the derivative of the inside material, which is 2x, all over x squared minus 4 squared, and then squared again. Wow. All right. So then this is looking a little bit ugly here, but think about this. Here we go. Let's now I've noticed I've got some x squared minus 4s in the numerator and the denominator here. So really what I've got in my denominator here, if you kind of clean up the denominator a little bit, x squared minus 4 squared to the second power, this thing is really just x squared minus 4 to the fourth power. All right, so instead of rewriting the whole thing, and the reason I'm doing that is because I can do a little bit of canceling here. Take a look. I've got an x squared minus 4 here. I've got 2 of them here, so I'm going to cancel one of them out there. I'm going to cancel one of them out here, and that's going to leave me with 3 of them left over. Okay, so I'm going to rewrite what I have left at this point. Okay, so I have 20 times x squared minus 4 minus, now I'm going to combine some terms over here. The x squared minus 4 is gone, so I've got 2x times 2, which is 4x, and 4x times 20x is negative 40x squared. Wow, negative 40x squared. Okay, and did I do that right? 4x, no, 80x squared, excuse me, 80x squared, there we go. All right, the denominator is just x squared minus 4 to the third power. And I don't want to multiply that out because that's just going to get ugly and messy. So cleaning up the numerator here, actually I can come down one more here. Cleaning up the numerator, I'm going to distribute the 20. That's going to be 20x squared minus 80 minus 80x squared all over x squared minus 4 to the third power, and that's all going to equal 20x squared minus 80x squared is negative 60x squared minus 80 all over x squared minus 4 to the third power. Wow. Okay. All right. So I'm definitely running out of room on this one, so I apologize if you're a little squeezed in here. I'm going to actually have to do some of this work off to the side. Now, my undefines are still x equals plus and minus 2. So right away I know I'm undefined at x equals plus minus 2. All right? But my zeros in this case are a little bit different. And again, since I ran out of room here, I'm going to have to find a place to do these. I apologize if you're running out of room here too. So I'm going to plug in 0 for y. We're going to solve for x. Now again, when you guys do this, one of the things you ought to know is that negative 60x squared minus 80. Whenever I go to find the zeros of a fraction, the bottom right hand side cancels out. Because when I go to cross multiply, this denominator is gone. So all I got to do is solve 0 equals negative 60x squared minus 80. Now, one of the first things I can do there, I'm going to go ahead and add 80, I guess. We'll do that. 80 equals negative 60x squared. I'll divide out the negative 60. So that's going to be 80 over negative 60 equals x squared. And, oh gosh, look at that. That's negative. I can't square root, but if I square root both sides of that, I got a negative inside the root. So there's no solution here. So we did all that work and there's no solution. All right? So I have two values that are undefined, x equals positive and negative 2. So those are my critical numbers. Let's go back up here. So I do have some critical numbers. So we'll go back over to our graph here, negative 2 and positive 2. So we're going to have to test some values again. So I can use the same values that I used for f prime of x. I'm going to use x equals negative 3. I can actually use x equals 0 in the middle. So we're going to do x equals negative 3, x equals 0, and x equals positive 3. All right? And this time we're looking at f double prime of x. All right, so here we go. I need to plug in, oops, this is supposed to be negative 3. So I need to plug in negative 3 into f double prime. Oh, goody. All right, take a look at my fraction here. Let's see what's going to happen. So if I plug in negative 3 to this fraction, all right, I'm going to get negative 3 squared, which is 9. 9 times negative 60 is going to be negative, and then I'm going to subtract 80 more. So I know that the numerator is going to be negative. Then I'm going to plug in negative 3 to the denominator. I'm going to square it, so that's going to be positive 9. Positive 9 minus 4 is going to be positive, and then I'm going to cube a positive, which is going to be positive. So that means that f double prime is negative from negative infinity to negative 2. All right, let's do 0. 0 should be a little bit easier here. All right, so we'll keep our little fraction bar there. Plug in 0 to the numerator, and I get negative 80, so that's going to be negative. Plug in 0 to the denominator, I'm going to get negative 4 cubed, which is also negative. So negative over negative turns out to be positive. Let's try positive 3. All right, one more time here. Plugging in positive 3 to the numerator, again, this turns out to be a 9 times negative 60 minus 80 more, so that's negative. Plugging in positive 3 to the denominator, that's 9 minus 4 again, which is 5, so that's going to be positive, so that's going to be overall negative. All right? And again, what we're looking at here is, what does that tell me about f of x? All right, so if f double prime is negative, that means that f is concave down. When f double prime is positive, f is concave up, and then concave down again. All right. Whew. I think we're ready to graph. That was a lot of work in there, wasn't it? All right. So if you look at the top of your paper right now, and you look at all of the stuff that we had for f of x, all right? So I'm going to start by graphing all of this stuff up here. My y-intercept at 0, 9 halves. My x-intercept at negative 3, 0. Uh-oh. No, those were... Yeah, negative 3, 0, and 3, 0. Okay. And then my vertical asymptotes at plus and minus 2, and my horizontal asymptote at 2. All right, so I'm going to start with all of that stuff right now. All right. So, y-intercept, 0, 9 halves. So let me grab a different color here. We'll go with orange. 0, 9 halves, so that's 0, 4 and a half. X-intercepts, negative 3, 0, 3, 0. Horizontal asymptote, we said, was y equals 2. So we'll throw that in here. Vertical asymptotes at negative 2 and positive 2. So we'll put those in there. And once we have all that information in there, then we can start to look at what is f of x doing. So f of x is decreasing from negative infinity to negative 2, and it's also concave down. So this horizontal asymptote tells me that as x comes from negative infinity, it's going to hug that asymptote, and it's going to curve down. So we're decreasing and we're concave down from negative infinity to negative 2. All right? So that's not bad. And then from, let's see, from negative 2 to 0, we're decreasing. But then from 0 to 2, we're increasing. So in between the two asymptotes, I'm decreasing from negative 2 to 0, and I'm concave up the whole time. So my decrease is going to come from above, concave up, until I hit 0. That was my y-intercept. And then I'm going to increase from 0 to 2, staying concave up. So there's the middle of my graph. And then the right side, We know that f of x is increasing and concave down. So we're coming up along the vertical asymptote and underneath the horizontal asymptote, and there is f of x. Wow, that was a long one, wasn't it? All right. Oh, and look, there's the assignment. We're all done. About time, isn't it? See you next time.